Hello, everyone, and welcome to today's webinar presentation, Beyond Jurassic NoSQL, New Designs for a New World, brought to you by ScyllaDB. I'll now introduce to you our speaker for today. We have Avishai Ish-Shalom, researcher and consultant. He can be found on Twitter at Nukemberg, at Nukemberg. Now I will give you his bio. In a world where anything has an API, everything is a software problem. This insight has guided Avishai Ish-Shalom throughout his diverse career, working on improving the complex socio-technical systems that create and operate modern software and promoting the use of mathematics in system design and operations. Spending 16 years in various software fields and capacities, Avishai has served as developer advocate for ScyllaDB, engineer in residence in Aleph VC, engineering manager at Wix.com, and co-founder of FewBytes. Currently, Avishai is an independent researcher and consultant. And with that, I will throw it over to Avishai, and we will begin the presentation.
Thank you. So today I want to talk about Beyond Jurassic NoSQL, New Designs for a New World. And basically this whole talk is about how old databases are and how they, let's say, fit in this new world that we have today. So the databases that we use today are pretty old. And when I say old, I mean very old. So the current generation of relational databases that you find in the field, like Oracle, Postgres, MySQL, that kind of stuff, it's about 30 years old. Postgres and MySQL the project started around 95, more or less, so they're both from the 90s. But actually the design architecture date back to the 80s, and even if you're talking about Oracle, it started around 78. So it's very old, and they have evolved. Some stuff did change, but there are limits to the original design that basically are still there. And some of those limitations are actually in the specification of the ANSI SQL standard. So it's very hard to circumvent that. So a lot of things changed from the 80s and the 90s. And just to give you a little bit of reference to stuff that happened that significantly changed the tech world. So Amazon, the cloud. Amazon launched it 2006, AWS, and GCP and Azure joined the party around 2013. So the cloud basically became mainstream about a decade ago, and that changed everything. Changed the operating environment, it commoditized software development, enabled a lot of the tech stuff that we do today. On the consumer side, iPhone launched in 2007, and of course, the internet changed immensely since we have smartphones. So that happened as well. Social networks and basically the explosion inside the internet, all sites we have, that all happened in the early 2000s. So for reference, Facebook launched at 2004. And just remember, like, databases were created before there was an internet. So this is how old they are. And it's very, I should say, even unfair to expect that those designs will still be will still match the use cases that we have today. And I think that they've done an amazing job, being able to still provide the service that we have today, even though the design is so old. But it does show signs of age. So what are we going to talk about today? We're going to talk a little bit about operating environment changes and changes in the business world and the business requirements of the systems. And then we're going to discuss briefly the architecture gap of legacy databases and what do we want from databases in this new world. And I'm going to give a few examples of how databases adapted and the ideas that we came up with and how that evolved, and of course the direction that I think that the future is going to bring. So let's start. Part one, partly cloudy. The reason I call this partly cloudy is because we all moved to the cloud, but the systems that we build on the cloud are mostly using the same mindset that we had when we designed for an actual data center. But it's not, everything's changed, of course, when you have cloud. So let's go back 20 years ago to 2002. everything ran back then on physical data centers. On premises or co-location, doesn't matter, but it was all physical, and basically we owned the servers. If you're running the system, probably you bought the servers or all the hardware actually, and maybe you rented it and you listed it from someone, but still it was usually owned. And the hardware that we got back then was special purpose. So it was enterprise grade software hardware, but we had different types of servers and different types of hardware for different types of applications or the database or whatever. So the database server was usually very beefy, had a lot of RAM, and usually was connected to a special storage array, something that was battery backed and had cache and maybe 2 tiers of storage, that kind of stuff. Usually devices that used to cost like $250,000 or even more. And this is basically what powered the databases back then. And the networks were dedicated. Not only were they dedicated for a tenant or for a specific system, they were also dedicated in terms of the links per the type of network that you had. So you had a special storage network, a special backend network, a special network for the application servers, and this allowed us to give a lot of guarantees to specific applications. For example, RAC, Oracle Application Cluster, had a special network that was called interconnect to synchronize the cache between the database heads. So basically what I'm trying to say is that a lot of the designer databases back then kind of assumed that you had this type of physical control over the hardware. And usually you ran in a single data center. Sometimes you had a few data centers, but we mostly use them in an active passive way, meaning that if we had a failure in the primary data center, then we failed over to the secondary. But it was very rare back then to see people running multiple data centers in an active fashion. Now, if you fast forward 20 years to now, everything is running on the cloud now. And yes, some people still have data centers, but the data centers themselves are being modified into a more cloud-like architecture. So we're going to have the data centers that are going to remain, they're going to be private clouds, basically. So the same architecture, same basic technology as a cloud, and it's all going to be managed as a cloud, even if it's a private cloud, which means automatically managed servers and shared networks that basically are separated with software. It's software-defined network now. And if you think about this, the networks on GCP and Amazon are basically, it's basically a public physical network that everyone is hosted on. And the thing that separates me from untenants is basically the AWS software. The storage is also different now. It's no longer specialized storage machines. It's not separate. It's either a local storage attached to the servers that I'm using, or it's a distributed SDS, software-defined storage. Think about EBS, for example. It's a cluster, a very large cluster of servers that Amazon are running. And yes, they have disks somewhere, but on top of those disks, there's a very large stack of software and caches and NVMe and stuff like that. We don't actually know the details; they don't tell us, but we do know it's distributed, and we do know that they replicate, and we do know that it's very complicated. And part of this we know because of postmortems of failures that they released. And all of this is running on commodity hardware, so it doesn't matter if it's a EBS storage server or the server of my database or the server of the application server that I'm using, doesn't matter. It's all basically the same hardware that nowadays the clouds are usually manufacturing for themselves, but they don't give you a special server for the database. They don't care. The database is running on a virtual machine. The virtual machine can run on any hardware, so it's all commodity hardware now, and virtualized, of course. And a lot of the people nowadays run on multiple regions or multiple clouds even, and even if they're not running on multi-region or multi-cloud, they're still running on multiple data centers, either availability zones or using external services like CDNs. So what I'm trying to say is that in the modern architecture, we have global infrastructure. Everything is running in more than one data center at the very least. So the other thing that changed significantly is hardware. Okay, so if you look at the hardware that we had 20 years ago, we had maybe one CPU core per machine, and maybe we had 32 gigabytes of RAM and maybe 100 gigabytes of disk, and the disk was magnetic, and there was a certain ratio of speeds, latency, between RAM and storage, RAM and network, and of course the network and storage. And this ratio basically dictated the design that we had for operating systems and databases and so on. For example, back in the day, the speed of the network in a single data center, it was about half a millisecond to contact a remote server. And the latency of a magnetic disk was 10 milliseconds. So it made more sense to fetch something over the network from a remote server that probably had this piece of data in RAM than to store it locally and get it from disk, because the disk was 10 milliseconds and talking to a remote server over the network was half a millisecond. But nowadays, in 2022, all this is different. Because of new technologies like NVMe, this balance has shifted. For example, the speed of network and storage is now completely different. With NVMe, the latency is measured in microseconds, and the latency of the network hasn't changed significantly. So nowadays, it actually makes more sense to store stuff locally than fetch it from the network. This table here basically summarizes the changes, and as you can see, some of those things have changed significantly. So the storage became about 1,000 times faster, which is quite significant, and shifted the balance completely. The bandwidth, relative bandwidth of RAM and storage also changed significantly, and the balance shifted, and you get the point. But the most major change that happened was an explosion in the number of cores. So Moore's law, everybody knows it. Moore's law basically came to an end around 2014. And when I say came to an end, Moore's law states that we get double the amount of transistors per the same cost every 2 years. And that is still going on. But instead of getting stronger cores, what we get since 2014 is more and more cores. And nowadays, you can the largest machines on the clouds have 96 CPU cores per machine, and this is only going to grow more and more and more. So you can expect to get like 200 CPU cores in 2 years, and so on and so on and so on. So this is a very interesting world that we live in. Now, when you're running in the cloud, everything is dynamic because everything is virtualized. And the time it takes to bootstrap new resources is basically it's almost immediate now compared to 20 years ago when we had to order hardware and we needed to wait weeks or even months for the hardware to arrive and then to install it and everything. So the lead time was very long. Now, if I want 1,000 more servers, I just put them up, a couple of minutes, I'm going to have them. So the virtualization changed everything when it came to the flexibility of resources. But it changed another thing. Because the resources are virtualized and because there's a lot of them, thousands of servers, tens of thousands of servers, and so on, so on, so on, they might also go away because sometimes they fail statistically, but also because I'm doing cost hedging. So spot instances on AWS, and of course all the other clouds have that as well. Basically, I'm saying I'm not willing to pay more than X for a server, and if the cloud provider, for some reason, they have more demand for those types of servers, then they raise the price of those servers and they take them away. So the end result is that for a variety of reasons, the number of servers keeps changing all the time, but not only that, servers can't go. So even if I have 10 servers all the time, it might not be the same servers. This is why we have autoscaling and capacity groups and stuff like that. If the server fails, a new one boots, you get the point. So the lifetime of a server has significantly shrunk. If 20 years ago we used to run servers for years and sometimes we didn't even boot them for years, now we're basically reprovisioning servers all the time, and some servers live like months, some servers live less than a day, hours sometimes. We just boot them when we need them and we throw them away when we're done. So the topology of both application servers and basically all the infrastructure that we have is constantly changing, which has a lot of ramifications when it comes to things like service discovery, for example, monitoring, so on, so on, so on, but also when it comes to databases. So I'll give you an example. I call this the ephemeral node conundrum. Basically, all the compute nodes on clouds are ephemeral, which means that they can go away at any moment, and that's not a bad thing because it helps with stuff like configuration drift and basically protects against different types of failures. But the problem is, how do we keep state? So the cloud provides replicated storage, basically EBS, or persistent storage on other clouds, as it's called. And it's nice because it allows us to keep that state when we move to a different node, or when we reboot a node. When you reboot a node on the cloud, it can be rebooted on a different physical server, but it's completely transparent because of virtualization. And as long as they have still the same state, then it's basically the same node. Okay, so you can think of node reprovisioning as basically a reboot taken to the extreme, because as long as I have the same disk, the same stateful storage, the same storage, then it looks like the same node. Doesn't matter if it was a reboot or a provision, it looks the same. So in theory, at least, it should be easy to change the number of nodes on the cloud. You just boot more nodes, and as long as you keep the state, then it's fine. But can you change it? Because a lot of the software that we have, and that relates to databases specifically, and actually anything that is stateful, don't really support this. With application servers that are stateless, it's pretty easy. We don't care about this. But when we're talking about stuff that has state, usually it doesn't support it. Maybe you need to reshard, you need to rebalance, you need to reprovision certificates, for example, for security or encryption, and you need to change your node configuration because you need to let the nodes in the cluster know that the cluster now has a different size and different keys and etc. You get the point. So when we're talking about stateful services, unfortunately, it's not so easy to treat nodes as ephemeral, which creates a lot of problems in cloud. And another problem is that the replicated the storage that the cloud gives us replicates to presumably multiple availability zones, and this is the specification that the cloud providers give us, that it's replicated three-way to different availability zones. But the databases that we use have their own replication layer. So what we get is we get two layers of replication that basically don't play well with each other. So think about the database that replicates to availability zone A and B, and it has disks that also replicate to zones A, B, and C. Now this is kind of weird because if availability zone C fails, which I'm not supposed to be on because my machines are located on AZ A and B, I might be impacted. And yes, the cloud provider kind of promises that this will be transparent, but we know from experience that sometimes it's not transparent because, you know, all abstractions are leaky to some degree. And also this has other problems. For example, performance. Okay, we have to wait for acknowledgement from all the underlying replicas, in this case, the disk replicas, before the database can continue doing its work. And it doesn't matter if it's abstracted or not, it's still going to take the same amount of time. Now, if the database had control over this, we could do a lot of interesting things. We could maybe batch the writes or stuff like this, and you could do this asynchronously. You could decide you don't want to wait for a specific availability zone, that kind of stuff. But because it's not transparent, because it's all opaque, then we can't do this. The cloud provider basically decides whether they want to wait for all the replicas to acknowledge or not, or if they want to fail a disk or not, and we have no control over this. So this creates performance degradation sometimes, and the worst problem for me, at least, is that it's not very debuggable. If there's a problem in the disk, all I see is that there's a problem in the disk. I don't know if it's because the disk itself is bad, or because one of the replicas failed, or maybe the cloud provider has problems in the storage network or whatnot. And then I have a very hard choice, which is, do I want to fail over to the secondary, to the backup? And if I do fail over to the secondary, then I might be losing some data that is supposed to be on disk that is replicated, but hasn't actually replicated to the secondary of the database. So the design where we do fsync, basically, we sync everything to disk, doesn't make sense anymore, because what we want is to fail between nodes, because this is control level. This is the language that the database now speaks. Okay, so the abstraction level that used to basically concentrate around controlling disk now doesn't make sense anymore. What we want is to control nodes. So this is just an example of what changed on the operating environment, but the business environment also changed significantly. So the most major change that happened in the last 20 years ago is, of course, the internet. So this is a graph of the number of users of the internet. And you can see that from the early 2000s, there was an explosion in the number of people connected online. So we went from almost 0 people connected to almost 5.5 billion people connected nowadays, which is like amazing. So if the database has had to support, let's say, a certain number of users back then, it was mostly on private networks and stuff like that. The number of users they had to support was measured in the thousands or tens of thousands. Now you're talking about millions, hundreds of millions, billions even. So the number of users that the databases have to support, and of course the number of connections, applications, as a result, has exploded to an insane degree. Now, this is not going to go on forever. At some point, everyone on the planet is going to be connected to the internet, and this will stop growing. However, other stuff will continue growing. Why? Because users do more. This is now the digital age, and if before, I used computers for certain things, now I'm using computers for everything. I'm connecting to my banks using a computer. I'm paying with a computer. Ordering a taxi with a computer. I'm doing everything with a computer. So the amount of digital services and transactions that I'm doing has also exploded. And also the software is doing more, and I have more devices. I used to have one computer in my house for everyone. Now I have just me. I have about 10 computers if you count, phones and tablets and laptops, and the Raspberry Pi I have for my media center and the smart TV and everything. So there's a lot more devices that are connected and consuming services. Those devices are also talking to each other. So even if the number of users will not continue to grow, will stabilize, the number of transactions, the number of connections, the number of operations that we do online will continue to grow and will continue to grow immensely. And this means more concurrency, more throughput, and very important for databases, more and more and more data. So we kind of have to assume that whatever database we choose, we were going to need to scale it for the years, during the years that it will be in service. Now, if this is not bad enough, everything is digital, but everything is digital everywhere. So we used to have this assumption of locality, that users kind of stay in the same region, which is why it was very easy to provide service from a local data center. But now users, they kind of move around the globe. They can hop on a plane, and in a few hours they'll be in a different continent, or they can just connect to VPN and they'll be on a different continent in a matter of seconds. They interact with each other globally. It used to be the case that that you did business mostly with local people, maybe once in a while did business with someone abroad, but now practically all of our communication systems connect people across the globe. When I'm on Twitter, I'm talking to people from Africa, from Europe, from South America, from America, wherever. When I'm playing a game online, I'm playing with people from around the world. So our infrastructure now has to support this kind of global connectivity, which is much harder because, remember, latency. And we're doing this using global infrastructure. So I mentioned this before a little bit, but nowadays, even if you have this small website, it's going to be serviced through a CDN. So you're going to have this kind of global network that that your service is working through, and you need to have local presence everywhere. And there's a bunch of reasons why you're going to have local presence. But the problem with this is that the speed of light hasn't changed, despite all the improvements in technology that we had. Throughput, increased immensely, but there's some physical limits that that we can't ignore. And maybe in a single data center, it doesn't matter so much because the distances are very small. But when you're talking about global infrastructure, this really matters. Okay, so the ping time from San Francisco to Tokyo, for example, is 100 milliseconds on a good day. Usually it's around 150 milliseconds, sometimes even longer. It fluctuates more or less. And this can be a problem when you have infrastructure that spans the globe, okay? So if you want to provide good service to your users, and when I'm talking about good service, it means low latency service, you need to have local presence, okay? So all of us have point of presence, which is basically the endpoints that the CDNs have, and it's no longer optional. And this is why CDNs became such a big thing. But there are other reasons why I need to do this. For example, data-intensive software, and this is increasingly the case with machine learning and the AI services, you need to process a lot of data, and you need to do this very fast and with low latency. So you have to store the data close to the user, and this means local data centers. And there are also regulations and data governance issues like GDPR and CCPA and stuff like this, which dictate that you need to store the data in a certain place. So sometimes having a local data center is mandatory just for legal reasons. So the end result is that modern systems usually have more the multi-home. They store data in multiple places in the world. And this means that we're going to have to deal with the latency between data centers. And this is no longer something we can ignore. And the databases that we had 20 years ago were not built for this because they kind of assumed that everything will be in the same data center and latency will be low and communication will be reliable. When we're talking about stuff that connects through the backbone of the internet, even if you're lucky and you're going through someone's private network like Google or Cloudflare or Akamai or whatever, the network is going to be congested at some point, and you're going to see some packets dropped. You're going to see connection interference and that kind of stuff. You cannot assume the network is reliable. The last thing I'm going to talk about when I'm talking about changes in the operating environment is that concurrency increased, and it increased for a number of reasons. We mentioned that we have a lot more users doing many more things using many more devices. We also mentioned that we have many more calls. What this means combined is that we have a lot more clients connecting to databases because we have many more API servers servicing many more users, and they run on more calls, which basically means more database clients that are using more and more connections. Now, if you ever used MySQL or Postgres or Oracle, you would remember that those databases were designed to have stateful connections that are very expensive. And when I'm talking about a connection being expensive, I mean that it's expensive to create a connection. It takes time, sometimes 300 milliseconds, 500 milliseconds, whatever. And it also consumes memory, both on the client side and on the server side, meaning on the database side. So there was a very strict limitation on the number of connections that those kind of databases could support. And what we realize is that we can no longer have this kind of restriction. And the other reason why there was this kind of limitation is because of locks. Relational databases were designed to enforce locks, and locks prevent scalability. And we're going to talk about that in a bit. So I'm going to give you a crash course in software scalability, and I hope it's going to be interesting for you. This is the Universal Scalability Law. It's basically a mathematical model created by Dr. Neil Gunter, and it describes how systems scale. The reason it's called Universal Scalability Law is because it's universal. It basically applies to any system. And the x-axis is load on the system, and you could measure that either in throughput or concurrency. Usually it's measured in terms of concurrency, number of clients connected. But it also more or less relates to the amount of resources that you add to server. So you could think about this as a concurrency of calls that are running your service. Okay. And the y-axis is the system throughput, the throughput that you can provide to the users, expressed in requests per second, or again, concurrent connections that you provide. Now, ideally, we would want linear scalability, meaning we add resources, we increase concurrency, and for every server that we add, we get, let's say, 1,000 more users serviced. Okay, and this starts off like this. You add more resources, you get more throughput. You increase the load, you get more throughput. But at some point, you start seeing diminishing returns. Okay, and why is that? Basically because of queuing. So you queue on locks, you queue on shared resources, and you can still see improvement when you add more resources. But for every the more resources you add, the returns that you get would diminish less, and you will get less and less performance from more hardware or more load. Okay, and at some point it's going to be so bad that it just won't be worth it adding more resources, and you will hit your scalability limit. But beyond this region, there's a region where that most people are not aware of, but does exist, and this is the retrograde scaling region, where you increase the load or you add more resources, but performance starts to degrade. You start to see a worse performance in the system, and you don't want to be in this region. And why is this happening? This is happening mostly because of excessive coordination or consensus. So if you have a consensus algorithm, if you're running something like Raft or Paxos, for example, those systems cannot scale beyond 7 nodes. Okay, because at 7 nodes, you will start hitting the retrograde scaling. This is like an extreme case of retrograde scaling, but you also see this on relational databases. If you're doing transactions that span a lot of records, then you will see retrograde scaling because basically the entire database has to agree on some invariant, and performance will start to degrade when you increase load. Okay, so you don't want to be in this region for as much as possible. So we try to avoid doing excessive coordination, consensus whenever possible. Now, basically, the problem of scaling is basically you can think of it as a problem of speed of light. We have to coordinate in a certain time over a certain space. So how do we deal with space-time constraints? It's easy. We have a warp drive. We basically warp space or time. So there's basically 2 ways to warp space, 2 ways to warp time, and this is the basics of all scalable architecture. And if you look at whatever architecture that is scalable, you will see that basically it's mixing those concepts in a certain way. So 2 ways to warp space. One is sharding and the other is replication. Sharding is basically dividing space into disjoint regions where you store every datum on a different shard. Usually this is done by giving every piece of data a key, and you can either split the range of keys, or you can just take a consistent hash of the keys and then do modulo X and have persistent assignment of keys per each shard. And the other way is replication, where you basically copy all the data to all the servers. And the problem with replication as opposed to sharding is that replication does require some coordination, at least in writes. Sharding, basically reads and writes are completely independent. With replication, the writes, you still have to write to all the replicas, and either you wait for all the replicas or one of them will lag behind. So there's a certain degree of coordination involved in writing, but the reads are basically completely independent of each other. So just to contrast the two, Sharding scales both reads and writes. It scales the data set as well, which is very important for large data sets. But the load is not uniform, not necessarily uniform. So you might hit performance limit on one of the shards while the other shards are not even busy, which is kind of a problem that we usually solve by having lots of shards. It's a shell nothing architecture, which also gives us some semantic limits. For example, you can do joins and you can do transactions. And if you need to do cross-shard transactions or joins, you need basically someone else's problem, and you need to move this up to a special subservice like a transactor or to the application itself. In a replication, all replicas are equivalent basically, and you can do joins or transactions because all the data is on the same replica. But it only scales reads. So if you want to scale writes, you have to combine it with sharding somehow. And it does require some coordination writes, as I mentioned, and it has the benefits of improving availability. Basically, if you lose one replica, it's not so bad. You still have other replicas, and yeah, we all know this. Now, when it comes to warping time, we have two ways to do this. One is we can lag behind. So we're using replicas. One of the replicas can be behind. This is basically known as asynchronous replication, or not, or we can wait for it. But if we allow it to lag, then we have warp time. You can think of it as basically stretching time. The other thing we can do is we can reorder. So if we have a log of operations, we can basically allow the operations when they replicate to other servers to replicate out of order. And this has a lot of benefits because then if we don't care about the order, we can parallelize as much as we want. So again, to contrast those two strategies. Lag is basically a synchronous replication. The problem with it is that it has limited parallelism. For every shard or replication log, because you need to preserve order, you can only have one stream of application, which means queuing and queuing latency, everything that is involved with queuing. Queuing has a very interesting performance ramifications. But it does give you one big advantage, which is deterministic results of operations. So the semantics are still the same as synchronous replication, except for the lag that you might see, meaning that you might see stuff from the past. As opposed to that, reordering, it removes the coupling between operations, so it gives us basically infinite parallelism, which allows us to fully utilize the throughput of network connections. It alleviates head-of-line blocking and the penalty of queuing latency. And because of that, it's also very resilient, because even if there's some kind of network problem and maybe you lost a few packets, then not all the stream is going to be delayed. Only the packets that have been lost and the operations that were in them will need to be retransmitted, and only they will be delayed. So it's more resilient in terms of how it deals with network failures. The problem with this is because of reordering, it's the results of operations are not deterministic because the order is not deterministic unless you have some kind of algorithm to sort this out. And this means that the application needs to be aware of this, and it needs to be designed in a very specific way to handle reordering, basically. So looking back at the Universal Scalability Law, we can now see how those strategies map to those regions of the USM. So shards, if you have shards and reordering, you're basically, it's basically a shared nothing system, and you can scale linearly almost infinitely. And that's amazing. This is like, if we could have the system, however we want, this is how we want it because it's infinitely scalable. If you're doing replication with lag, okay, basically a synchronous replication, then you will have some coordination overhead, and you will get to this coordination region of diminishing returns. If you're doing sync replication, which basically means you're not doing any of the warps, you're not doing time warps, you're not doing space warps, then you're going to have retrograde scaling, and this is something that you cannot avoid. So that's very unfortunate, and this is something that you can only do if you're talking about databases, if you're running on a single data center or some other network that has very low latency and it's very reliable. So now that we understand scaling a bit more, we can talk about how modern databases evolved to handle those issues and build new architectures that utilize those scaling strategies. So what do we want from a modern database? We talked a little bit about the changes in operating environment, and they dictate very different requirements for modern databases. For example, we want databases that support dynamic topology, so we can utilize ephemeral cloud nodes and that we won't have problems when the cloud takes away a compute node, for example. We want the failure domains of the database to match those of the cloud. The abstraction the cloud provides is of nodes, availability zones, and regions. And we want failure domains that also match this. In other words, we don't want to care about disks because the disks are now abstracted into servers and availability zones. So we want databases that don't rely on the disk being available when they boot. We want databases that rely on different nodes on different availability zones surviving whatever outage there was. We want read and write scalability. Why? Because we talked about how data size, the data set is only going to grow, the user count is only going to grow, and of course the concurrency is only going to grow. So we need scalability. We also need CPU scalability because hardware is changing and the servers of the future are going to have more and more cores. And of course, also the servers of today have what I think is already an insane core count. So we need databases that can utilize those cores. We also need geo-replication because, like we said, data is going to be spread globally and speed of light is not going to change. It's not going to improve. That's not happening. We need to support high concurrency, many more connections than we support now. And of course, because the topology is dynamic and we're going to use a very large number of nodes, we don't want to deal with configuring and managing them manually because it's impossible to manage 1,000 nodes manually. Okay, the amount of people you will need is insane. The chances that there will be some mistake are just, it's basically 100%. So this needs to be done automatically. And we also want the cluster itself to be managed automatically if possible. What do I mean by this? If, let's say, a certain node fails, I want this node to be replaced automatically. I want the database to self-heal when a new node joins, automatically expand its capacity, and so on, so on, so on. So this is what I want from the modern databases. And unfortunately, 20 years ago, no one provided this. But then we started seeing new databases that tackled some of those challenges. So the original databases, like I said, assumed physical infrastructure, but they also kind of assumed that the servers themselves will be monolithic. And if there was a failure, the way that we handled failures is we basically rebooted and recovered. And when I say rebooted and recovered, this sometimes took a long time. You needed to reread the transaction log and reapply it, and it sometimes took several hours to do. So we can settle on having downtime as a recovery strategy, which in the modern business world is no longer an option for most services. And also, most databases require special hardware, which is again not really an option when we work in the cloud and you cannot dictate what hardware will be available. We talked about stateful connections and CPU scaling and all that stuff. And the really important thing to remember is that replication in the old databases was basically an afterthought. So it didn't support asynchronous replication very well, and of course it didn't support stuff like reordering. But the newer databases that we started seeing a few years ago already had some of that stuff. So first example is MongoDB. MongoDB came out in 2009, and it had native sharding and synchronous replication, which allowed it to scale to the diminishing returns region, which was also already much better. But the major problem with how MongoDB handled shards was that the shards were basically coupled to nodes. And when I say coupled to nodes, I mean two things. If you wanted to move a shard, you basically needed to replicate the state of the entire compute node, including the identifier or whatever. And the second thing I mean is that the size of the shard was basically the size of the node. So if you wanted to change the size of the shards, you needed to basically reprovision the entire cluster and have new compute nodes with different size. That was kind of horrible, and it was a management nightmare. And the cluster management itself was manual, so you needed to if you wanted to add or remove replicas, you need to do this manually. Every change that you needed to do, whether it was shards or replacing nodes or whatever, was manual. It was very annoying. The topology was basically static. And because of this, MongoDB was limited to a very small number of small clusters, basically, small amount of nodes. So, okay, that's not really a problem if we can run on very large nodes, right? But we couldn't do that either because the internal architecture of MongoDB had a lot of locks, so it couldn't scale very well to machines with a very large core count. Now, Cassandra is a very interesting database that originally came out around 2008, but it took a while before it was usable. And before version 1.2, it still had coupling of shards to specific nodes. In version 1.2, which is why I mentioned giving this one as an example, they removed this, and this is the first time we had a database that was, at least in theory, almost infinitely scalable. So it had both time warps, it had sharding, it had replication, and it also had reordering. So at least in theory, it could do linear scaling to a very large degree. And it also had a very large number of small shards. And this had a lot of advantages, both in terms of how the load was distributed across shards, so the load was more uniform. And yes, you still had hotspots, but it was less of a problem. And also you could move shards between servers, which was a very novel innovation, and made the cluster management a lot easier, and also replacing nodes. And because basically when you add a node, you needed to rebalance, but you didn't need to move all of the shards of nodes. You only needed to move, just parts of them, and the shards that you did move were relatively small. So this is the first time that we had some support for dynamic topology, but changing the cluster was still painful for a number of reasons. The primary reason being that copying data, the reshuffle procedure, took a very long time because we couldn't saturate the network. But from this point in time, we started seeing large clusters, and we still have very large clusters of Cassandra. Nowadays, thousands of nodes, tens of thousands of nodes, and so on. And it also supported Gale replication, so you could run multiple clusters on multiple data centers, and this actually worked well in an active fashion, which is amazing. The major problem with this is that Cassandra could not use nodes with a very high core count. And why is that? Because the internal architecture, which is basically threads and memory mapped files, this is an architecture that has a lot of locks, and because there was a lot of locks, so if you remember the USL, this is the diminishing returns area of scaling, and in some cases you also needed to have consensus between the cores. Some locks are basically synchronous, and this brings you all the way to the retrograde scaling region. So in practice, you can scale beyond, let's say, 32 cores or so. And this is still a problem with Cassandra even to this day. This is where Scylla came in. So Scylla 1.0 was launched at 2016, and it had all the goodies of Cassandra because it's basically the same external architecture, but it did have two additional advantages. One is that it solved the CPU scaling issue because it has an internal architecture of sharper core architecture, which Scylla talked about in a number of webinars that you can find online if it's interesting to you. I also talked about this kind of architecture in a number of talks and different conferences. And because you could finally do a CPU scaling, you could run on very large nodes, and also the other benefit was that Scylla actually has automatic node configuration. When you run Scylla on an instance, it basically benchmarks the instance, it identifies the hardware automatically, and automatically configures the right parameters for you, so you don't need to start fiddling with how much memory you need to give this cache, how much memory you need to give the buffers, and so on and so on and so on. So node management became much easier, and because of those two changes, something very interesting happened, which was we could saturate the network when we do rebalance or reshuffling. So changing the topology became less painful. Okay, so it's still kind of annoying, but now when you remove a node, this procedure takes, instead of a few hours, it can take less than an hour. Okay, so it's much easier now. And you can run larger clusters on larger nodes, so scalability is much better now. Now, the relational database world, of course, also evolved. So this presentation will not be complete without mentioning relational databases. So I just gave CockroachDB as an example. CockroachDB has native sharding and semi-sync replication, but instead of sharding using persistent hash, it shards using ranges, which is very interesting. And the shards can be changed. The size of the shards can change. It's called tablets. And also they're decoupled from servers, so they can move between servers when necessary. So you can deal with dynamic topology because of this. But the cluster changes are still somewhat painful because you need to copy data in a certain way, and because CockroachDB provides ACID guarantees, it needs to maintain certain, let's call it invariance over the replicas. Basically needs to make sure that all replicas are up to date. So it cannot be as scalable as something that does reordering or has lag, basically. So it's doing one of the time warps and partially one of the time warps. It can sometimes do the lag time warp, but when you're using transactions, it needs to be synchronous to a certain degree, so there are limits to its scalability. This is by design, so it can provide the ACID transactions. It's still very impressive to see that you can provide ACID transactions on a distributed system. But if you look at the benchmarks that, for example, Scylla and others have done, you will see that it doesn't match the scalability of NoSQL, which is it's, I guess, pretty obvious, but still amazing that you can even scale ACID database. So that's great. Now, looking into the future, Scylla 5.0 is coming out this year, and it did one very interesting modification. This is part of a project called Project Circa, and what they did basically is they moved from uniform sizes of shards to dynamic shard sizes, like CockroachDB tablets. And basically now the sizes of shards, basically shards will be split or merged depending on how much they're used, basically on the load and the size of the shards. And this improves scalability and also makes changing the topology much easier. So now with Scylla 5.0, the topology is going to be practically dynamic. You will be able to add or remove nodes almost at will. The modification procedure will be much easier, much faster, and it will allow you to run on very large clusters and all the other benefits that Scylla already gave. But it also has one very interesting change because of this, which is that they removed reordering. They removed the reordering timeline, time warp. So I mentioned before that the reorder time warp is what enables linear scalability. So isn't that a problem? Turns out that it's fine. First of all, application developers find the semantic changes of reordering very hard to deal with. So when you remove the reorder time warp, you're making application developers' lives a lot easier. And it turns out that a lot of the modern architectures are based on ordered data anyway. If you're using Kafka or something like this, then you're already forcing order. So this makes this kind of change very native. And the other thing is that network throughput, if you remember the ratios that I've shown before, has improved so much. It's improved by a factor of 40 since 2002 that actually parallelizing through shards is enough to saturate the network in most cases. And unless you're running very, very, very large clusters, in most cases, this shouldn't be a problem. And because you can also split shards a little too big, you can kind of fine tune this and deal with this. So in practice, for most cases, this shouldn't be a problem. And I think that it's kind of amazing that we can do this trade-off nowadays. So I'm personally not happy yet. Despite all the improvements that we got, and despite all the amazing databases, modern NoSQLs that we have now that provide all those things, there are things that I want for future databases that have not been supported yet. So this is my personal wish list. First of all, I would want connections to be cheaper, to be much cheaper even, if possible, stateless. HTTP3 support would be amazing because then it would be very easy to write database clients. And also one very interesting feature of HTTP3 is that new connections are basically free. So if you don't know about this, go read about the quick protocol. It's very cool. So this is what I would want. I would also want distributed tracing because a lot of the modern architectures are basically microservices, and in microservices we have distributed tracing, and it kind of stops when it comes to the database because databases don't support this. So I would want databases to support distributed tracing so I can see a transaction spanning the entire cluster and the entire system through all the microservices all the way to the database. I would also want burst capacity because there's always some kind of variance with load and capacity throughout the day. So I want to be able to utilize lambdas, for example, serverless as extra capacity, or just add servers that won't have to replicate data. So I want to be able to add capacity within minutes, if possible. And likewise, I would want to be able to store all data or compressed data on object storage because it's much cheaper and allows me to scale my data set more and more and more. And lastly, I would want clear policies. I would want to be able to say something like this data set can only be stored in Europe, or this data set can only be stored in Europe, but only on low priority storage, for example. This would be very helpful for a lot of applications. But to my knowledge, no database supports those yet. And I'm hoping that in the next 5 to 10 years, we will see databases that support this. So if you have something in your personal wish list, then I would be very interested in hearing your opinions on this.
All right,
So
Avishai,
thank
thank
you very
you
much.
for an excellent presentation. I'm sorry to cut you off, but we are at the top of the hour. Unfortunately, we won't have time for Q&A, but you see the contact information there for ScyllaDB. And this has been a great presentation. DZone would like to thank Avishai for doing an excellent job. DZone would also like to thank ScyllaDB for providing our audience with a wonderful webinar. Lastly, thank you to everyone who attended today, and we hope you learned something new that will help you in your developer career.